You are sitting in grade 11 physics class. The teacher writes 3 letters on the board, EMF, and a formula underneath it. You copy it into your notebook without thinking too hard about it. Faraday's law. It will probably be on the exam. You memorize it, you move on. Here is what nobody told you in that classroom. That formula, the one you learned on a Tuesday afternoon, the one you highlighted in your notebook and half forgot by Friday, that formula describes the single most important discovery in the history of human civilization. Every light bulb that has ever turned on, every phone that has ever charged, every power station on Earth, every electric motor in every machine ever built, all of it flows directly from one law, the law you already know. Michael Faraday spent 14 years getting to that formula. 14 years of failed experiments, wrong guesses, burned hands, and notebooks full of dead ends. He had no formal mathematics education. He was a bookbinder's apprentice who taught himself science from the books he was paid to bind. One of the most brilliant experimental minds who ever lived, and he was fumbling in the dark for over a decade, trying to find something you already have written on page 47 of your school notebook. You sat in class, and this felt ordinary. It was not ordinary. What if you took that knowledge right now, today, and went back?
London, 1820. The air tastes of coal smoke and river mud. The Thames carries everything the city throws into it. Streets are lit at night by gas lamps, flickering, hissing, unreliable. The fastest thing on earth is a horse. The idea of sending power invisibly through a wire to light a room or turn a wheel exists in absolutely no one's imagination. Not one single person on this planet has conceived of it yet. You are standing outside the Royal Institution on Albemarle Street. Inside, a young man named Michael Faraday is bent over a workbench surrounded by coils of copper wire, iron bars, glass jars of acid, and a battery made of zinc and copper plates stacked in salt water, the most advanced electrical technology in existence. He has just read about a Danish scientist named Ørsted who discovered, almost by accident, that a wire carrying electric current makes a nearby compass needle twitch. Faraday is electrified by this. If electricity can affect a magnet, he reasons, surely a magnet can affect electricity. He has been trying to prove this for months. He wraps wire around an iron ring. He connects it to his battery. He watches the compass needle. Nothing. He tries different configurations. Nothing. He tries for weeks. Nothing that lasts. He is missing something, and he does not know what it is. What he does not know, what no one on earth knows in 1820, is this. A steady magnet does nothing. It is the change that matters. This is the exact concept from your grade 11 physics class, electromagnetic induction. It is not the presence of a magnetic field that creates electricity. It is the changing of a magnetic field. A magnet sitting still next to a wire, nothing. A magnet moving through a wire coil, current flows. The faster it moves, the more current. The moment it stops, nothing again. Faraday will not fully understand this until 1831. That is 11 more years of searching from where he stands right now. You have known it since you were 16. The tools available to you in this room right now are everything you need. Copper wire, Faraday has rolls of it. Iron bars and iron rings, a galvanometer, a sensitive needle that twitches when even tiny currents flow through it, a bar magnet, and the battery, a crude but functional source of electricity. No plastic, no printed circuit boards, no oscilloscopes, just wire, metal, magnets, and a needle that moves. Every person in this building is ferociously intelligent. Faraday himself will one day be considered one of the greatest experimental scientists who ever lived, but every single one of them is staring at this problem from the wrong angle. They are looking for a static effect, a presence, a field that simply sits there and pushes. You know they are wrong, and you have known it since a Tuesday afternoon in grade 11.
You walk to Faraday's workbench. You pick up a coil of copper wire, maybe 30 turns wound into a loop the size of your fist. You connect both ends of the wire to his galvanometer. The needle sits at 0. Faraday watches you, curious. You pick up the bar magnet. You hold it completely still inside the coil. You both look at the needle. 0. Nothing. Faraday nods. He has tried this. You can see the mild disappointment already forming on his face. Then you move the magnet. Slowly, you push it deeper into the coil. The needle jumps. Faraday inhales sharply. You hold the magnet still again. The needle returns to 0. You pull the magnet back out. The needle jumps in the opposite direction. You do it again. Push in, needle right. Hold still, 0. Pull out, needle left. You look at Faraday and say, it is not the magnet that makes the current. It is the magnet moving. The electricity only exists while the magnetic field is changing. The moment it stops changing, the current stops. The change is the cause, not the presence, the change. Faraday sits down. He's very quiet for a moment. Now you show him what this means. You wind a second coil of wire around the same iron ring he was using earlier. 2 separate coils, not connected to each other at all. One coil you connect to the battery. One coil you connect to the galvanometer. You tell him, watch when I connect the battery, not after, at the exact moment I connect it. You touch the wire to the battery terminal. The galvanometer needle kicks, then settles back to 0, even though the battery is still connected and current is still flowing through the first coil. You disconnect the battery. The needle kicks again in the opposite direction, then 0. You explain, when you connect the battery, the current in the first coil goes from 0 to full. During that change, the magnetic field it creates is also changing, and that changing field passes through the iron ring and induces a current in the second coil. But once the current reaches full and stops changing, the magnetic field stops changing, and the current in the second coil disappears. The same thing happens in reverse when you disconnect. You write the relationship on a piece of paper in the simplest form you know. The induced voltage is proportional to how fast the magnetic field is changing. Faster change, more voltage. Slower change, less voltage. No change, no voltage. Faraday reads it again. He picks up the magnet and moves it slowly through the coil, watching the needle. Then faster, the needle jumps harder. He laughs, a short, astonished sound, and does it again. In the next hour, the two of you wind a larger coil with more turns of wire. More turns means the changing field cuts through more loops of wire, adding up the effect. The needle swings harder. You tell him, this is how you make the effect stronger. More turns, more coils, faster movement. You have just handed Michael Faraday the complete operating principle of every electrical generator that will ever be built. Hydroelectric dams, coal power stations, wind turbines, the charging cable sitting next to your bed in 2026, all of it runs on this, on the changing field, on the thing you demonstrated in 10 minutes with a magnet, a coil of wire, and a needle. Faraday stares at the setup on the bench for a long time. Then he looks at you and asks, if we spin a coil of wire continuously inside a magnetic field, the field is always changing relative to the coil. Does the current flow continuously? You smile. You tell him, yes, and that is how you will power the world. If your understanding of Faraday's law is solid, and it should be by grade 11, you just handed Michael Faraday the discovery that took him 14 years in under an hour, with a magnet, a coil of wire, and a needle. The knowledge that changes everything in 1820, you already have it. Every high school student in 2026 carries more understanding of electromagnetism than Michael Faraday had after a decade of his best work. The question is, do you know it well enough to actually use it? Because now you know what it's worth.